So thank you, Matteo, for the introduction. So today I'm going to explain to you the concept of a new ultra-low power and high sensitivity Resonant Micromechanical Receiver, or RMR, and is analytical description and the numerical optimization of the system. So I'm going to tell a slightly different story. I think everybody in this room heard about the Internet of Things. So in the future, a lot of devices will be interconnected. So we'll have sensors talking to each other, sharing data, and providing solutions, hopefully, to make our life easier. So the last data I saw forecast 1 trillion devices, not good, of course, but like sensor inside products by 2035. And the sensor, of course, they need to monitor the RF environment to capture the signal that needs to trigger them to provide what they're meant to be, or like they are designed to do. And if we leave this kind of screen on, this RF sensing on, we are going to drain the battery in a few days, probably 1 week, a couple of weeks. So the problem is like with the state-of-art technology. For this reason, research is actually addressing the problem to develop wake-up ready receivers that can detect a very, very low amount of power, so high sensitivity, with almost no power consumption. We are talking about 10, 20 nanowatts, which is almost the leakage rate of a battery. And thank you to the colleague of mine that explained this picture before. But as you can imagine, if you have devices in a war zone, changing a battery every 2 weeks is a problem. So we want to extend the life, for example, of this unattended ground sensor to years to make sure that like we don't need to act on them and like go and dig them out, for example. Of course, ultra-low power wake-up ready receiver, they are not a novelty. They have been out there for many, many years. But like if you look at the plot of the sensitivity that they can detect and the power that they require to detect that amount of power, we can clearly see a threshold that has been broken only last year by a receiver that showed minus 69 dBm with a power consumption of 5 nanowatts. So what we need to do is to act on the RF front end to get actually to push this threshold down and be able to get to higher sensitivity with a lower power consumption for the aim I described before. Our goal actually, and the one that I'm going to use is to reach minus 80 dBm with a power consumption of 10 nanowatts. So the system we are actually describing, that I'm actually talking about, is asynchronous RMR that actually has to detect a 50% OK modulated signal. And the target sensitivity that is minus 80 dBm, which is equal to an equivalent voltage source of 71 microvolts. And the antenna here in this model is represented like by a 50 ohm impedance. So the first block of our system is actually a lithium niobate resonance voltage amplifier. It's a counter mode resonator. And its aim is to provide a gain to the input of a MEMS demodulator made in CMOS technology that actually generates a current that is sensed by the CMOS transimpedance amplifier at the output. As you can see, we are not yet to the point where we are proposing a monolithically integrated system, but our aim to get the best performance is to realize the demodulator and the CMOS block on the same chip with the same technology, and then interface the lithium niobate resonator through wire bonding. We are also trying to change this approach to reduce the parasites, but like this is not going to be included in this presentation. So let's look at the block one by one. The MEMS resonant voltage amplifier is made by X-cut lithium niobate, which provide an incredibly high KT square, 32%. I don't think we can do better than this, and show in the past good Qs, so we can get an incredibly high figure of merit. And the frequency of operation has been identified to be between 50 and 400 megahertz, which is a range of interest, especially due to the availability of some RF spectrum around 100 megahertz, and could be helpful for the Internet of Things. So this resonator enables to match to 50 ohm if we really need it, because in this case we're doing voltage sensing and not power sensing. We can do high frequency filtering, so the wide response actually, as you can see here, is going to get rid of all the components that we don't need from the carrier signal. And then it can provide passive voltage amplification to the input stage of the demodulator that it is modeled as a capacitance. So this is the equation for the gain. As we can see, don't look at the math, but it depends by the gain that we can provide, depends by the capacitance, it depends by the real part of the impedance at the frequency of operation. And here, I basically plot some expected gain for different technologies piezo technologies with different level of KT square. And we select the X cut because overall, even if the Q is lower, it provides really, really good gains. So once we set CD, the only parameters that we need to select are basically C0 and the frequency. The MEMS resonant demodulator is electrostatic driven, so we can use actually the nonlinearity between the input voltage and the force generated on the device by the comb, send the drive comb at the input to generate a current at the output. And in this case, we can just extract the component of the OK demodulation at a lower frequency, which is actually the resonant frequency of the demodulator, and turning into a current that can be sensed by the transimpedance amplifier. Other than that, we can also do a low frequency filtering. And of course, the aim is to maximize the current at the output. In this case, frequency of the modulation, CS and CD, which are the capacitance of the sensors for the drive comms, are the only parameters that we need to select once the technology is identified. Then we have a CMOS transimpedance amplifier, which aim is to sense part of the IX generated by the demodulator, because I'm going to lose some in the parasitics, and provide gain to the rectifier. The rectifier is, we have the transimpedance amplifier, then we have a source follower that drives a passive latch rectifier. That is actually the component which provides the wake-up signal to the sensor after this wake-up radio receiver. And of course, in this case, we want to maximize the output voltage. The latch rectifier triggers for about 40 millivolts. We can decrease this threshold by increasing the number of stages until this capacitance introduces a problem in the generation of the signal. And of course, we are going to sacrifice the latching time in this case, but this is another approach that we can take into account. So let's go down to the optimization. First of all, we need to select the frequency of the carrier and the frequency of operation of the demodulator and of the transimpedance amplifier. And if we select actually for a fixed quality factor of a resonator, we can see that basically they are not much dependent by the frequency of the modulation. They are just dependent by the frequency of the resonator. So we want to work at a lower frequency. But if we take into account that here we have a modulated signal that actually needs a bandwidth, and if we set that bandwidth, 3D bandwidth to be the frequency of the demodulator, then the maximum quality factor that we can get from the resonator is going to affect the frequency of the modulation. For this reason, we select the lowest frequency of the modulation. There is one problem working at 50 megahertz because the devices that we use are going to become extremely bigger. So for the optimization, I've used 100 megahertz. Now once we select the frequency, we just have the capacitances to select. Don't look at the math, just look at the dependency. For the gain, we want basically low CD and high C0 to reduce the resistance of the resonator. For the current, we want both CS and CD to be big, even if we have a term that depends by the pulling voltage, but we don't really care about it. While for the voltage, until this resistance is smaller than the impedance of CS, we can go up with CS. And as a result for the optimization, we can see that for CD and CS, I plot the V output at the output of the transimpedance amplifier. And this is for any optimized C0, and we can see that we are way above the 40 millivolts required for triggering. The gain does not depend on CS as we were expecting, and the point of operation was identified around CD of 500 femtofarad and CS 3 picofarad. The surprising thing is that the resonator does not work at the point of theoretical gain because there is a trade-off between CD and the current at the output of the demodulator. And once we select CD, we can go in the plot that relates CD with C0 and select the C0 to size the resonator. One of the most interesting is scaling the gap in the demodulator is going to strongly affect the output voltage. What can we take from this presentation? That this technology can be scaled down to a huge range of frequency, allowing us to do also multi-channel. We can implement different modulation methods. And an aggressive scaling of the technology, considering that we have nowadays, can bring down even to more than minus 100 dBm, down to even 100, minus 100. That's what we hope. Okay, and this is all. I would like to say thank you to my colleagues, to the staff of the NanoFab and DARPA for funding this project.